Right. Good morning, SQA. We had a nice conference dinner last night. Thanks for the supporters for that. And yeah, we have 2 more sessions to go, and then the conference is over. First session is benchmarking and enabling software, and this is, of course, once you have your chip and it's working somehow calibrated, and well, it needs enabling software to be calibrated, and you also have to benchmark it to be able to make it better and to see like how good is it in possible applications. So we thought this is a very important topic, and we have many companies, people working on that. So we will see very good talks on that topic. And then, of course, design and modeling is extremely important, extremely valuable, because when the chips become bigger and bigger, it takes more and more time to do iterations, and the better your design and modeling is, the faster your development is. So this is why we chose also these 2 topics to be in the scientific sessions of the conference. But having said that, I'm happy to ask Yonathan Cohen from Quantum Machines to chair the benchmarking and enabling software session. So please, Yonathan, it's all yours.
Okay, good morning, everyone. I hope you had a great time last night. So welcome to this first session today about benchmarking and enabling software. I think that, yeah, as Mikko said, as we move up the stack from the control hardware, or from the quantum hardware and then the control hardware, then the control software and the software in general is starting to become more and more important, because we kind of need to, at least at this stage of the game, build a stack in order to kind of squeeze every bit of performance from the underlying hardware. So I think we have really great 3 talks about this subject today. So our first speaker is Michael Biercuk, a professor from Sydney University and co-founder and CEO of Q-Control, and also a collaborator and a good friend. He will tell us about how to improve performance dramatically in superconducting qubits processors using deterministic error suppression.
So thank you. I'm gonna try this because I really struggle to stand still when I give talks. As the intro alluded to, first of all, I'm the person who gave you the headache you have this morning. So thank you for making it out. I'm going to tell you about work that we've been doing at Q-Control, focused on enabling software that can derive performance benefits, really, as Yonathan suggested, to eke out every bit of performance that is effectively hidden in the hardware. The work is done by this team. You'll find both Pranav Mudada and Andre Carvalho are in the audience. They gave posters yesterday. And I'm going to speak specifically about a bit of technology called deterministic error suppression. So this is a little bit different than some of the things we heard on, I think, day 1, or the first full day, about probabilistic attempts to cancel errors. This is a slightly different approach, and I'll tell you how. So this is roughly the outline. I'll give a little bit of the motivation of our work and who we are. I'll talk about 2 specific building blocks of deterministic error suppression relating to how we use AI agents in closed-loop fashion to redesign quantum logic operations on superconducting machines. I'll talk about crosstalk elimination at the circuit level, and then I'll put the pieces together and explain how they ultimately derive benefits. And I do want to point out that all of the experiments I'll show you today are based on the long-standing partnership we've had with IBM. Who are we at Q-Control? We're a company that's focused on building what's called infrastructure software. So we build software that touches the controllers, the technology from our friends at Quantum Machines or Qblocks or Keysight, and goes up to connecting to applications, algorithms, and the like. We provide everything in between, and specifically for a technical audience, we focus on things like error-robust quantum logic, AI-driven closed-loop optimization of hardware, system characterization, error-robust compilation, and the like, and all of our tools are technology agnostic. The motivation for what we do comes from the realization that it really has been control engineering as a discipline that has built more or less every industry today. And it builds absolutely my favorite. These are the systems from Boston Dynamics, one of the coolest companies in the world in my view. These are robots that can walk and dance and stand up stably even when somebody hits them with a hockey stick. And it's because of dynamic stabilization. It's because of the technology of control engineering. And the lesson that we derive is that autonomous systems focused on control can give us stability and ultimately the performance we want out of otherwise unstable hardware. That is the motivation. That is the theme for what I'll tell you about today. Now, the starting point for those building blocks that I'm going to tell you about is redefining quantum logic in order to give improved performance at the gate level, at the hardware level. Now, I think the notion is reasonably simple. It was alluded to in David Mackay's talk and a few of the other talks. We have quantum logic operations that are somehow defined by a light-matter interaction. In superconducting qubits, this is typically some kind of microwave operation. The microwave operations are now going to be redefined with modulation in the time domain. The purpose of the redefinition is to provide the mathematical transformation that you want for a particular logic operation, say an X gate or a Z gate, but also to provide cancellation of Hamiltonian terms that are unwanted. Say you have some unwanted detuning or unwanted over-rotation error. You can design the control such that those Hamiltonian terms can be canceled. If you're familiar with NMR, this is like composite pulsing. But we know that this bit of work has given a huge number of benefits demonstrated. So first, we know, and we have shown on IBM's hardware in this manuscript on PhysRev Applied, that you can cancel coherent or correlated errors. You can reduce them by about an order of magnitude. You can improve the calibration window up to a week. That is, you can have the same pulse definitions for a week without needing to rescale them. You can reduce inhomogeneities by an order of magnitude. That is, from device to device, what is the best performance? You can smooth that out, which is very important for error correction. You can reduce error correlations. That is, the statistical properties of the residual errors can be changed by this virtualization process, if you will. And quite importantly, this technique and all the other techniques I'll talk about today have zero sampling overhead. You don't have to repeat the same circuit 20 or 50 or 100 times and then average in order to get error suppression. You just implement these controls and the errors are less likely to occur. Now, I have on here see Andre's poster, but really at this point it means go and talk to Andre because the poster was yesterday. What I want to talk about now is one approach that we have used to perform this redefinition. There are obviously lots of ways. You can do it numerically with a model. You can do it analytically. But I want to talk specifically about a case here where we have unknown Hamiltonian terms. How do we perform gate optimization? How do we redefine the waveforms that are relevant when we don't actually know what the system is in totality? Now, this is commonly encountered when we have a real device and we go from a computer model-based representation of our system to the real system. Because in the real system, as soon as we output something from our numerical generation package, it then has to be output by an arbitrary waveform generator or DDS or something like that. It has to be sent down control lines. It has to cross over packaging, enter the quantum system, and ultimately the Hamiltonian that you achieve in the time domain could be very different than what you expect. And this is an example. These are the measured dynamics. The different colors are the projections on a 2-qubit subspace. I think the thing that you can see is you kind of squint at it and it's a giant mess. The idea is that the dots, the markers, don't match the lines that are associated with them. This is the dynamic simulation of a 2-qubit cross-resonance gate compared against the measurement of the dynamics of the 2-qubit cross-resonance gate derived from a Hamiltonian model that's provided by the backend. The dynamics just don't match. And so when the dynamics don't match, what can you do? Well, one approach that we took in this paper that was in PhysRev X, Quantum last year, is to perform a closed-loop optimization. Now, this is nice because it actually obviates the need to have a complete system model. You don't have to have a mathematical representation of the Hamiltonian. All you need is an agent that can connect to the machine itself. And in this particular approach, in the loop, what we see is that we can perform measurements on the quantum computer. We can feed those measurements into the agent. The agent can decide what to try next. This is the notion of closed loop control. But more specifically, what we did in this particular experiment was look at something called deep reinforcement learning. And in deep reinforcement learning, we have that same general closed loop, but you'll see on the right-hand side there are two branches to the loop. Because one interesting characteristic of reinforcement learning is not only does it try to optimize some objective function, like minimizing infidelity, which in this particular case involves maximizing a state fidelity and also minimizing leakage, but it also, that's the reward, it also gains intermediate information at different times by measuring state observables for incomplete gates. So it performs a partial gate. It asks, what did that partial gate do in terms of a state transformation? And it uses that knowledge in order to build up in this cycle. So this is the approach that we took for the cross-resonance gate. What I'm showing on the middle panel here is the default cross-resonance gate implementation in Qiskit Pulse on IBM's system, which involves 3 different signals. The top signal is a single qubit, effectively a chain of pi pulses. Then U1 here is the control signal that actually implements the cross-resonance interaction. And there's a classical cancellation tone called D1 here that's used to cancel some classical crosstalk. Now, we asked the agent to find us a new definition via this closed loop optimization in runtime. So I want to be clear, this is not offline based on a model, simulate and come up with a control and then try it. This is interacting in runtime with the hardware. And we end up with a gate that has some different form. Notably, it does not include this classical cancellation tone. But the modulation that you see here gives you gate performance that is superior to the T1 limits in a measurement protocol that involves simply repeating the gates. You see that as you repeat the gate a number of times, as we've seen in some previous talks, the error grows more slowly than the default implementation. Now, this was a fun experiment in lots of ways. It was a 20-dimensional optimization of the I and the Q signals that are used to modulate the microwaves. We preserved in this particular instance the overall echo-like structure, but that's not a hard constraint. The point here is that we were able to achieve the T1 limits for the gate, and we were able to do that routinely. But also, this idea of closed-loop optimization, which is handled with no human intervention, it is just the agent determining what to do, is easily parallelizable. So in the devices to which we had access, we had up to 16 qubits. This is a chip called Guadalupe from IBM. And here what we were able to do was take that closed-loop optimization. It happens in this experiment to be a different agent. It's not DRL. I think it's either Gaussian process or simulated annealing. But the overall view is the same. And we could have multiple agents in parallel, up to 5 at a time, optimizing gate pairs. And then we could step through the different pairs such that you didn't share a qubit in any particular optimization step. And at this point, I think the current status is in 6 minutes, we can fully re-optimize the entire chip. We can redefine all the 2-qubit gates on the chip and get those canonical, factor of 2 or 3 performance benefits relative to the default implementations on the hardware. There are some other nice benefits, like the agents tended to learn robustness because we didn't control when the IBM hardware would be recalibrated. Sometimes the calibration would be interrupted, would interrupt the training, and our agents would find controls that were robust against that interruption. So we ended up with some solutions that were still better than that day's default a month later, with no retuning of our protocol. The next part of this is to look at errors that occur not just in the individual gates, but also in the implementation of the circuit. Because if you look at more or less any algorithmic implementation, you see that in addition to whatever the gates are that you're implementing, there are often long idle periods, right? From a quantum logic perspective, they're just identities. We typically write them as just blank spaces on the circuit diagrams. But those are places where errors can creep in. I think this is broadly well known. This is one paper from Dieter Suter's group that looks at adding dynamic decoupling. Daniel Ladar has done a lot of work on interleaving dynamic decoupling into protocols as well. But we took on this particular task asking, how can we make the best identity operations to cancel errors that arise at the circuit level and only at the circuit level? So that means we're not only considering dephasing, but we're considering what has been spoken about quite a lot, the canonical ZZ crosstalk, the always-on interaction that can lead to errors. So what we are exploring in this particular experiment is looking at what happens when we allow 3 different qubits in parallel to evolve. The black line is you don't do anything during an idle period, you just wait. We all know that leads to some dephasing. It can be from global dephasing. The next is what happens when we apply a standard dynamic decoupling protocol. These are echo-like sequences. For the experts in the room, it happens to be a 2-pulse car per cell. When you do that, you get some benefit across all the qubits, but not that much. However, when you replace them with a new protocol, that is, it's actually shown in the top right, that is involving not only pi pulses, but pi pulses that are offset in time based on what's happening on neighboring qubits, you're able to cancel crosstalk. You're actually able to, if you're from this background, you're actually able to decouple this term in the Hamiltonian that you don't want. And when you use that particular protocol, you end up with a decay as a function of time that looks much more like T1, right? So our overall approach to integrating this into circuits involves, first of all, trying to maximize T2, so reduce global dephasing, then maximizing the suppression of ZZ crosstalk, and reducing the accumulation of X gate errors. So we're aware of what the error is in each pulse. You don't want to just keep banging away with pi pulses if they make things worse. All of those things, in a context-aware manner, are fed into a routine that decorates the circuit with dynamic decoupling in a way that is context-aware, right? So this is the other building block that we have. And now for the rest of the talk, I want to put these pieces together in one workflow. The overall approach that we've taken is to make, well, we have very flexible tools in the background, but to deliver this as a zero config offering, where all we do is we take as input a CASM file, we handle all of the infrastructure software aspects, connect to the back end, and give you back an answer. Now what's actually happening in there is the following. We have a pretty conventional approach to compilation. Some of you may have seen this on the poster yesterday. We add an error-aware hardware mapping. IBM has something similar. It's called Mapomatic there. We have a slightly different version of that, where we map the circuit to the underlying hardware based on understanding of the error rates. Then we start adding things that I talked about today, the circuit crosstalk elimination and the gate optimization. All of those things are added. At the end, after execution of the experiment, we perform our own version of measurement error mitigation, which scales as order 1 in the number of qubits. That is, it does not involve scalable overhead. So what happens when we implement this? Here is an example of Grover's search. What you expect on the left is shown on the left, excuse me. You have a marked target state. You expect the output of the machine to reveal the location of your needle in a haystack. What you get when you use a very well-configured system is the top right. The biggest peak in the distribution is not the answer you're looking for, but when you add in this additional bit of infrastructure software, which is one line of code, you end up with the bottom. This is experiment. This is from a real hardware system accessed via the cloud. Right. So in some cases, the transformation can be binary. It goes from giving you the wrong answer to giving you the right answer. Quantitatively, the benefits that we see are up to many thousands of X improvement in algorithmic execution on the machines. This is the Bernstein-Vazirani algorithm. It's finding a hidden bit string. The particular experiment we're performing here is asking to find the all one bit string, and then we just ask how well we succeed in that routine. There are 3 bars here. The first, the purple is Q control with our technology that I just told you about. The default is just compiling with a very aggressive compiler. It's the level 3 Sabre compiler for those of you who know. And then at the bottom, the expert tune adds the native Qiskit dynamical decoupling and their very effective M3 measurement error mitigation process. But by the time you get to about 9 qubits, we're 100 times better than the default, and we get up to a circumstance at 16 qubits in terms of the circuit width, where in no case in execution of the default do we, in 32,000 attempts, get the correct answer, and we get to about 20 to 40% in our experiments. You can look at the same data another way, and I think this is probably the most important slide in the talk. This is the same success probability now on a logarithmic scale. And I've added 2 things at the top. The proxy measure predictions or projections for what you should have achieved. So one comes from just tallying up the gate errors from the back end, and the other comes from saying, how long is my circuit and what are the tallied T1s? And what you see is that the typical approach down here in black, the default, is orders of magnitude away from what the proxy measures tell you should achieve. When you add these coherent error mitigation or coherent error suppression deterministic strategies, you push yourselves way back up to the proxy error bounds. We can also demonstrate explicitly that using these technologies we can improve quantum volume. So this is a quantum volume measurement conducted on IBM Guadeloupe, where measuring these heavy output probabilities, we're able to increase the quantum volume from 32 to 64. We just barely miss getting it to 128. But it is a demonstration that at the lowest level, the hardware is improving using these coherent error suppression strategies. I'll show you quickly two more examples. One is QAOA. What I'm showing here on the left is the simulated landscape as a function of the two QAOA parameters, gamma and beta, where you have whatever the complex landscape is. When you actually do the measurement point by point of what the energy landscape looks like, with the default configuration, what you see is on the right. By eye, it does not look very similar. You can actually use something called a structural similarity test from image processing. It really doesn't look anything like the standard landscape. But if you replace that with the deterministic error suppression, you get almost a 30x enhancement in the structural similarity of those landscapes, which is, of course, very important for when you execute the QAOA. Quickly, we can do this to quantum error correction because it's just an algorithm too. In a 5-qubit demonstration, we can improve the ability of the syndrome to correctly identify an added error in the red box over all the different syndrome measurements. And then I want to end here by saying that improving algorithms is not the only thing we do. We also have quite a lot of emphasis on how we can use closed-loop optimization to characterize systems, so completely autonomous system characterization. These are experiments based on an optimal Bayesian update. I think we'll hear about more similar or related work in the next talk, where again, in a closed loop fashion with no human intervention, you can perform parameter estimation, saving orders of magnitude in the number of measurements. So I'm going to, at this point, stop, tell you that we've given you a little bit of an insight about how automated processes from quantum control and deterministic error suppression can give you many orders of magnitude improvement in the performance of quantum algorithms. And these things go neatly together with the future of quantum error correction, adding deterministic approaches to the closed-loop feedback coherent approaches in order to get ultimately the fault-tolerant performance we want. So I'll stop there. Thank you all, and point you to our documentation site if you'd like any more information.
Thank you, Mike, for this very impressive talk. So we have a couple of minutes for questions. Yes.
Thank you. I am curious about how that agent looks like.
The agent for the closed-loop optimization. Sure. So, in the particular experiment I showed, this is a deep reinforcement learning agent. It's a policy gradient agent. There are many, many different versions of this. It's based on neural networks, so I think it's 5 layers in this particular approach. I will point you to Pranav, who's in the back, who can give you more insight into the details of the agent if you were interested. So raise your hand, Pranav.
Thank you.
Over there.
Thank you. Maybe you could just repeat how does the calibration effort scale as a function of the algorithm complexity?
So do you mean this part, or do you mean the very last thing I showed?
I would say in general, because I can understand that this pairwise gates you can maybe this you can do once, but if I have a gate sequence, how long? Sure. How much extra effort do I need to do?
Yeah, so the optimized gate replacement is done in that parallelized fashion. You can parallelize across the entire chip. We stayed with 16 qubits because that's the biggest machine we had access to from IBM at the time. 6 minutes. It will scale with the number of parallelized steps you have to break it into, right, based on the topology, the connectivity of the qubits, right? The circuit crosstalk is deterministic, right? It's an algorithm that just determines, based on the context, what do I do to add dynamic decoupling. The compilation is probably one of the heavier parts. It's an optimization problem, but that's generic. As circuits get much bigger, you have a bigger optimization space, and this is one of the things that we focus on. And then one nice thing is that the particular version of measurement error mitigation we use has fixed overhead in terms of calibration measurements. It's based on neural network approach. It captures correlations between the measurement error readouts on neighboring qubits, but it doesn't have the exponential or even the linear scaling of the EM3. It's order 1.
So let's say I wanted to have 1,000 quad qubit on computer. Do I need a server rack just to run this?
I mean, so all quantum computers have server racks next to them. No, you don't need a supercomputer to do this optimization. These are things that you can do on your laptop right now. As you scale up, workstation is generally appropriate. But we do, in all of our tools, we do cloud access provisioning, so you can parallelize as much as you want. Classical compute is super cheap, right?
Okay, I think we have to move on. So thank you, Mike, once again. Okay, our next speaker is Anurag Roy, and Anurag is the Chief Product Officer at Qruise, coming out of Jülich, and he will tell us about Bayesian methods for adaptive characterization of superconducting devices.
All right, so thank you everyone for coming up on a Sunday morning after yesterday's conference dinner. And thank you to the organizers for such a fantastic conference. So I'm Anurag. I work at Qruise and Forschungszentrum Jülich and the University of Saarland. And I work with the group of Professor Frank Wilhelm Mock in optimal control. And today I'm going to tell you a bit about what Michael already alluded to towards the end of his slides, which is how do you estimate parameters for your system model, and how do you do that in a way that is scalable. So when you have a new quantum device, the usual process that you will undertake is that you have model-based optimal control, which is what you will either do yourself or your in-house theorist or your theory partners. They will come up with some pulse that has been optimized based on, I don't know, grape or something. And you take that pulse and you go to the lab and you see, OK, it does more or less good, but not great. So then you go to the next step, which is what you want to do. You want to calibrate these pulses on hardware. And we heard a lot about this in the previous talk, that how do you make this process better. Typically, we'll have, so this is what you will do classically. You will have something like orbit, and then you do gradient-free optimization. So in the previous step, you had a model, which means you had access to gradients, and you could use something like a gradient-based optimizer to optimize the pulse parameters. In this case, you use something like a gradient-free optimization. So what are the problems with these approach? So optimal control can be only as good as your model, because when you are doing the whole open loop model-based optimization, it all depends on how many of the device imperfections do you model into the whole dynamics that you have been playing with. And the fewer sophistications that you model into it, the less accurate your final pulse will be. The hardware calibration, as we have often seen, it can take time. So you are given a new chip. If it's a 100-qubit chip, it can take weeks to months. And often a very good example of this is that we saw a very big chip from IBM towards the end of 1 year, and it wasn't until multiple months later that we actually had proper calibration numbers on the different gates for that chip. Because calibrating a new chip that's fresh out of the fab does take significant amount of time. So what do we do? Now, for optimal control, of course, you can have a better model, right? You can just continuously keep funding more and more PhD students to come up with more and more complex parts of your model that you can use to get better pulses. And you can do that, and we have done that, and of course, you get increasingly better matches with your actual hardware. And then for calibration, you could have better optimizers. So we have tried many different classical optimizers, as well as reinforcement learning optimizers, where an agent is actually learning how to best tune your optimizer. And we heard a lot more about this from Michael, about how do you scale this process to do something better. But that's not enough, because even after you have done some very good calibration of your system, that still doesn't mean that you know very well the model that you were using initially. And you want to learn, what did I go wrong? So which parts of my model were not properly estimated when I started with this process? So that's where learning from data comes, right? You want to learn from the data that you have collected during the calibration process, that how do you improve your system model? And the very simple steps for this would be that you save the data that you obtain during the calibration, because so you don't need to perform a whole separate process. You're already doing calibration, which means you're collecting data from your hardware. You're running an experiment and collecting a data that can form the foundation of your machine learning process. And then you do gradient descent on this, and then profit, right? Because, well, you have learned something about your system. That's a very broad simplification, but you get the idea that if you have data, the idea is that you do not want to throw this data away and you go back after a week and start from the same step. What you want to do is you want to use this data to learn system parameters. And in the very simple cases, you can learn things like the qubit frequency or the qubit anharmonicity, and that's already great. That's already something that many of the labs are not doing right now, and we should be pushing more towards using this data for learning system parameters. But so this would be a typical workflow for this. You do optimal control. You use some form of digital twin for this purpose, and then you get the data, and then you use that data for model learning. But this is still not good enough. And why is this not good enough? It's not good enough because, so I mentioned that we're using the calibration data, and we're performing machine learning on the data to learn your model. Can we combine these two steps? And what if we want to learn some arbitrary parameter? This is important because, so typically, we perform this set of textbook experiments, right? Experiments that your PhD supervisor learned from their supervisor, and that has been going on for ages now. And we use these to learn different system parameters. But what if there is a parameter for which there exists no textbook technique for learning them? What do we do at that point? And what is the most efficient way? I think this is something that's very crucial, that most of the techniques that we have right now, they are heuristics-based, and they work, and they have been working for decades. But do they have any information theoretic founding that that is the most efficient way to learn a particular parameter? So that's a question that we need to ask, because as we scale our devices, this will become more and more important. Because even if they are okay-ish when we are doing for smaller systems, when they grow, when the systems grow, if our techniques are not the most efficient ones, they will not scale. And how do we learn several parameters at the same time? So the bottom line is that the textbook techniques that we have, they're great when we have 5 qubits, 10 qubits, 20 qubits, but not so great as we go towards 100, 200 qubits. And what we are proposing as a solution to that is to adaptively learn from the data. So this is what I'm going to talk about today. I'll spend the next 5 to 10 minutes explaining what I mean and what are the challenges and where are we with the implementation. So Bayesian adaptive experiment design. Given a system and a system with a model, what we want to do is we want to devise the optimal set of experiments that can constrain certain model parameters of that system within a given tolerance bound. And how would you go about doing this traditionally? Traditionally, you would do a set of experiments, you would analyze the data, and you would fit the model to the data to basically reduce some error bounds, maybe some sigma or some Gaussian, and this is how you would go about doing it. How do you do it adaptively? So in adaptively, we want to use the data to direct what next steps we should take. So here, you will do one experiment, you will analyze the data, and you will choose the next experiment. This sounds like a slow process, and I'll go over which parts of this can be slow and which parts of this are not slow. So if we want to make this more mathematical, we want to formulate the problem properly. So we have some prior on our system, that we have some PDF that it's a Gaussian with some width of the sigma. And we have a bunch of available controls. So typically, this can be that I have pulses which can be parameterized to a certain degree. I might have 20 parameters, 30 parameters, depends on what level of control you have on the hardware. And I also have some likelihood that given this control parameterization, what output do I get? So this likelihood, it can be in the form of a closed form equation, or you might have an actual system model. So you might be actually solving the quantum dynamics, the differential equation, to get this likelihood. So that means this likelihood can either be explicitly given as a closed form equation, or it could be implicitly in the form of some differential equation that you solve. And our goal is that you want to find the optimal controls that can reduce the uncertainty in your prior theta. OK. So how do we go about this? So at this point, you go back to your high school Bayesian systems, and of course, you want to calculate the posterior. And once you calculate the posterior, then you want to calculate the information gain. So this information gain is at the core of the experiment design process. And you can choose many different types of information gain functions. It could be something like this, what we use here, which is the change in the entropy. Typically, it could be also something simpler, like you just want to measure how much did the sigma of your Gaussian change, how much did the width of your Gaussian change. It could be something like that. And once you calculate this information gain, you want to calculate the expected information gain, which means that you have a broad range of your theta parameters, and you want to calculate, assuming all of these theta, what is the expected information gain that I can gain from my system by performing this experiment. So this is what you get. This EIG is the expected information gain for this particular set of model parameters. And then you want to optimize for the maximum information gain, because, well, that will let you know that particular parameter to a certain degree of uncertainty. So what I need to focus on, or also maybe make a note of, is that theta could be a vector, which means you are not bound to just learning one parameter at a time. Theta could very well be a vector of 20 dimensions, as big as you want to be. And here it's only constrained by the classical compute, because all of this is happening in the system. This is all happening on a classical computer in the model. So as you can see, this is the bad part, right? That's like multiple integrals going on, and that's definitely slow, and that's compute heavy, which is why, even though Bayesian adaptive design has been known for several decades in information theory and control engineering, it's not until recently that we started using it more and more. So one of the common approaches that people have taken in the last couple of decades is to use variational inference. So when you use variational inference, you basically try to approximate this ugly-looking ratio with these techniques, and that gives you some kind of performance gain. And it's commonly used in chemical engineering, in process plant systems, where you want to essentially identify different plant parameters to optimize and get, well, more performance. What I'm going to talk about is to use deep adaptive design. So this is work done with our collaborators at the University of Oxford, where their idea or their suggestion is that given a system that I am modeling with certain parameters, I can use a reinforcement learning agent to essentially learn what experiments to perform. And this might sound like, OK, you have an RL agent and you're shoving it everywhere. That's not it. This problem maps very well to the common use cases that we see for reinforcement learning agents, which is, given a certain environment, estimate the best policy to gain the maximum award function that you can gain, which is, again, what we are doing here. We have a certain environment, and we want to learn certain models to a degree of coherence, and we want to do that with the best possible policy. So this is why policy learning, similar to what Michael was describing in the previous talk, is also a very good agent for this problem. Now, the problem here is that we are still doing some of the integrals. We didn't get rid of all the integrals, because what you see here is that we are learning this policy offline, which means I have to do all those integrals offline, and then when I deploy this model to my quantum device, I can say, OK, fine, my model has learned now those integrals, and it doesn't need to do that. But what if I don't want to do those integrals at all? So then you can use a reinforcement learning agent for that as well. You can use a reinforcement learning agent not just for predicting the best policy that will allow you to perform experiments for the maximum information gain, but you can also use a reinforcement learning agent to essentially estimate that density ratio that we saw in the previous slides, which looked ugly. And that makes this thing very computationally affordable when running on real experiments. And what we want to understand here is that this process essentially amortizes the cost. So the cost of training the system is something that you can do upfront, and you can deploy this model. And once you deploy this model, then inference cost is very, very low, which means all of your work is done upfront, and you can do it once. You can train it on several systems and do it once. And then you deploy the model, and then it works on multiple systems. And there is no further need of of retraining it if you're using it just on superconducting systems, for example. So where are we? The conclusion is that you can use a reinforcement learning agent to predict the best controls that can define experiments for maximum information gain. We have promising initial results on the superconducting hardware at the Forschungszentrum Jülich. That's actually hardware from IQM. And what we want to do going ahead is that we want to explore different neural network architectures. So right now, what we have been using in this are something called LSTM models, long short-term memory models, which are common in cases where you have some sort of time-varying activity. We want to try out more and more newer models because we believe that will allow us to better estimate these quantum dynamics. And what we believe will be really useful is to see how many simultaneous parameters can we learn over time. And this is important because as we'll have more and more chips that are growing in size, this will be the main bottleneck, that how do we learn different parameters at the same time, because we cannot spend weeks learning parameters sequentially. And I think Adriaan will talk a little bit more about where this bottleneck comes into the picture. All right, so thank you for your attention. I work at Qruise, as I mentioned originally, and I must make this compulsory, this plug that we are hiring. And talk to me if you want a demo of what I just showed. We can set up a demo for you. We can set up an integration for you. Yeah, thank you.
Sorry. OK, so we have a couple of minutes for questions. Yes.
Thank you for a very nice talk. Could you just say a little bit more about what freedom you give in the controlled design space? Are you giving arbitrary control over waveforms? Are you changing only times? Any constraints? I'd just like to hear some more.
Right. So we have tried a few. For example, we have tried parameterized pulses, which are essentially Gaussian pulses, where you have some parameters of the Gaussian that you can vary. But we have also tried completely piecewise constant ones, which are like essentially all the parameters are as many pixels as you have in the pulse. And from early results, it seems that this piecewise constant does give better results, probably because you have more parameters to play with. But we also have some ongoing work where we're essentially focusing on sparse controls, because we want to have fewer parameters, because that's good in terms of everything. So even though we have seen initial results, we believe there is some benefit in focusing on work that uses sparse controls and essentially has much fewer parameters.
Thank you for a very nice talk. You showed using the orbit as a cost function for your optimizer. And then optimizing the pulse parameters for information gain. Have you also considered optimizing the quantum circuits you run for information gain, similar to what you're doing, say, in gate-set tomography?
Not yet, but that does sound promising. Yeah, something to do, I guess. We have not done that, no.
Thank you. It was pretty neat. This optimizer is a classical optimizer. Why not a quantum reinforcement learning optimizer?
I think it's a circular problem, because what we'll do is we'll use this to get the good quantum computer and then use that to do the better optimizer. I'm just joking. I think that the reason is because we don't have quantum computers that do proper RL yet.
OK, thank you.
So I have a short question.
Yes.
So it looks like you're optimizing on the information gain, basically. Is there any trade-off between kind of exploration and exploitation, kind of, maybe not moving in the direction to maximize gain of information, but moving in the direction where we think the parameters are actually,
Yeah, so there is, I think, of course, a trade-off, as in any of these reinforcement learning tasks, between the exploration and exploitation. We leave it to the agent to learn that over time, because you can essentially optimize for that as well. You can have several trials and help the agent figure out which is the best policy to take. But yeah, so to answer your question, yes, and the solution would be to let the agent essentially optimize through that trade-off process.
So the reward is not just the information gain, then it has to be a more complicated function then, no?
Yes and no. So you can design because I think the information gain itself is already accounting for the fact that you will find the parameters which are best suited to the model. Because only then will your sigma become smaller, because that happens in line with the hardware. So what I mentioned originally, that you do an experiment, that you get some data from the experiment, and then you do the next run, right? So if you don't get the data, then of course you are doing all on simulation. But if you get the data, then the data is that indicator that, yeah, this is the right direction to go.
Okay, thank you.
Yeah.
One more question there.
Hi. Hello. Very nice result, actually. Can you probably comment about, probably I missed this just now, but you mentioned you want to kind of test simultaneous parameter learning. But these techniques that you mentioned, what you expected to be like, how much is it more advantageous compared to the traditional calibration techniques that you mentioned in the very first few slides?
Right. So I believe there it's basically saying that we don't even have a traditional approach because we are not yet working with systems that are 200 qubits long. So it's not that we have a foundational or some baseline to compare to. Typically, what we see with like 5 or 6 qubit devices is that this can easily be several times faster. But I don't think that's a fair comparison, because that's not where these methods are actually meant to be really applicable or really attractive. So I think once we get to the 100 and 200 qubits, where every lab has a 100-qubit chip, which is not yet the case. We only have a few companies which have that. So once we get to that stage, that's where we will see a lot more that how does this scale with the bigger systems. I think right now, the promise is purely based on the statistical learning theory, that this is a more efficient way, but not based on actual large system baselines.
Okay, thank you very much.
Okay, so if we don't have any more questions, then let's thank the speaker again. Okay, so our next talk is by Adriaan Roel. Adriaan is the co-founder and director of R&D at Orange Quantum Systems, and he will tell us about how to solve the bottleneck of characterizations.
Thank you, Jonathan. So indeed, I will be talking about tackling the quantum chips diagnostic bottleneck. But before I do that, I want to introduce a bit why we care about this. So I think to anyone in this audience, it's obvious that quantum computing is becoming a reality. I've put a few recent highlights: the first quantum computers in the cloud, the hallmark demonstration of quantum supremacy or quantum advantage, as it's sometimes called. But if we're really honest with ourselves, quantum computers are not yet reaching their potential. So I'm showing here the results of a study by Lubinsky et al. Based on volumetric benchmarking, and maybe that the numbers look a little bit better if we use some of the techniques that were shown earlier in this session. But I think we can all agree that although we're now really reaching a threshold where we cannot do things anymore completely classical, we're also not yet fulfilling this promise of this quantum computer that's it's just going to do what it's supposed to do. So what are the challenges that are preventing us from realizing that? And I know you can make this in several different ways, but on a very high level, I think if we look back at this conference, there were 3 main themes going on. We talked about quantum applications, quantum algorithms, and especially how can we find something useful to do in this era. Another one was a central theme in multiple sessions was the system integration challenge. How can we find device architecture that scales? How do we deal with the I/O problem? How can we calibrate all the systems simultaneously? But I think really the most fundamental of all of these is quantum chip development. Can we get higher coherence, higher yield, all in architecture that scales? And I think that's the most important one to focus on, but I'm not a fabrication engineer, so I don't know what to do in the clean room. But what I do know is I know how to measure these systems. So what we're doing is we want to make a system that's not optimized for quantum computing, that doesn't scale to thousands of qubits, but is optimized for doing very fast characterization of qubits. And I think if we're looking at this problem, we'll realize that it's slightly different than what we're used to in a traditional semicon characterization, because we're not just measuring transport properties, but we need to actually also tune up our qubits before we get the relevant quantum information metrics. And that brings me to the next question. What information do we really need to know? And I made this figure a couple of years ago, but you can really think about it in 3 distinct steps. So the first one, that's usually an indicator of how well your device is going to perform, are just measurements you can do at room temperatures. These are typically material properties we can measure. I put 2 recent references, both from this year. I saw another work by IQM in this conference about room temperature JJ probing. Now, measuring the room temperature resistances and then using a magical number to predict qubit frequencies is fairly common practice. But the reason I highlighted these works, and also the one I saw earlier this week, is because this is really the first time that we're talking about statistics. So this is really the first step in going beyond the hero devices and really saying, how can we move this to an industry scale process? And then the one that I personally am a lot more interested in is the cryogenic measurements. What can we do at cold temperatures? And this is really the point where it starts to deviate from what's done in the conventional semiconductor industry, because we need to start doing all sorts of experiments consecutively. And then the level beyond that is once you go to the quantum information property. And I think that one's especially relevant to also go towards, because if you go back to the figure I showed 2 slides back about the volumetric benchmark, I think one of the main lessons we see there is that the gate fidelities we reach for the qubits in isolation are not really a good predictor of the performance at scale. So if we really want to be able to iterate on the designs of our devices, on the fabrication methods, and see what works better, we also need to go to this level and look at crosstalk measures at scale, or maybe even also the volumetric benchmarks. And then when we look at it, we actually see that analyzing quantum chips today is as complex as controlling a quantum computer. So in order to do all these things, which we're just doing for the purpose of testing quantum chips, we need to actually build a full hardware system. It needs to cool to 20 millikelvin, isolated from the environment, typical shielding requirements, control lines, the control hardware by the many manufacturers that are also in the room here. And if we go to the next step, we need to think about, okay, how can we do multiple devices per cool line? Can we make it faster to exchange them? And the other side, and that's what this particular session is about, the enabling software, are the diagnostic protocols. And besides just what the software should do, I put another one there. That's the operator requirements. And currently, I think it was briefly mentioned that IBM had this amazing device that there was still several months between when they announced their 100-qubit device and when it's operational. And that's because there's still an awful lot of semi-manual operation and tuning in there until it gets to the point that the tools from, say, Q-Control can take over and really take it to the next level. And right now, the people that do this still need to have a PhD in physics. I think that's a problem because we want to scale to beyond that. The other thing I'm showing here briefly is this dependency graph. Now, this is a fairly common technique, but it shows just sort of the complexity of how all these protocols are connected before you can get to well-defined gates where a lot of these techniques work. And then if we're looking for the next steps, we need to always be one step ahead of the process of record. We want to parallelize it. We want to move to wafer scale, those kind of things. So what can we do? What can we do if we want to tackle the diagnostic bottleneck? And I think the first step to do, rather than just rushing forward and going for it, is realizing what we are trying to do. And there's different moments where you need different tools. So I think we need to be honest. So if we're looking at the first step, in the research phase, you don't want to automate things. If we're still figuring out new qubit designs, these protocols don't exist. You want to be flexible. You want to try whatever it is before you start bringing out the heavy guns. So you want to be very flexible. And I think this is also the point where, yes, we do need PhD level operators. But then once the device becomes standardized, once you're talking about, hey, we're now iterating on the material properties of our transmon or on the size of our capacitor plates, well, then you can standardize it. And then once you say this is kind of what we're going for, and you move into industry, then it makes sense to start fully automating it and pushing for high throughput. So then what's required at these different levels? At the first one, we just need a typical lab setup. You might want some control framework so that you don't have to reinvent the wheel. And this is where a lot of the tools that are out there are useful. The next step up, that's where it makes sense to standardize things. There's something a lot of labs do in-house, but also something that's now commercially available. And then if you want to move to the automated step, we're going to hit another bottleneck. So one thing that you might not realize is that if you're making a large experiment library, you test all this on your quantum setup, on your quantum hardware. But at some point you realize, hey, I want to try this really cool thing I saw in this paper, but you are at the risk of breaking something else. And you need to go back to actually testing it in the fridge. And at some point, your system becomes so unmanageable that you cannot iterate it anymore. And this is the moment where a system emulator is really required. And that's also something I'll talk a bit in detail. It's not required if you want to push the envelope, but if you want to automate it and scale beyond what we can do as individuals, you're going to need these tools to develop against. And then if we're going to the optimized step, I think that's really what we're going for in the end. You want to think about the advanced calibration protocols, the advanced machine learning approach, somewhere presented earlier in the session, and also optimizing the hardware setup. So then we're talking about having wafer probers cryogenically, but then compatible with flip chip architectures. That's all future dreams, but it's a very relevant thing to be aware of that these things are coming up. So going back to the theme of this session, enabling software. So if we're looking today at the quantum software stack, it looks a bit like this. And the good news is there's an awful lot of really good open source frameworks out there. And they're well maintained, well documented, state of the art, best scientists in the world are pushing them. So why am I talking about this? Because all of this is based on a top-down quantum computing-based approach. And what's really missing there is a good way to deal with what we are dealing with in this room, which is the experimental physics side of it. And that means that this layer right there is typically overlooked. And because we needed the tools that are much closer to hardware, we developed Quantify. It's an open source framework. I invite everyone to take a look at it. We did this in a partnership with Qubits. And it consists of two parts, Quantify Core, which is all the basics for running experiments, measurement loops, live visualization, data storage, etc. And Quantify Scheduler, which is a unique hybrid control model that allows you to control both quantum gates and pulses. And I should also mention that we have support for multiple hardware backends, so we're compatible not just with the Qubits hardware, but we're also working with Zurich Instruments hardware, and a Keysight backend is under development. Let's go a bit more. So I want to go into a bit what is it that makes this framework special, and especially about the scheduler. So since we started developing this, I know that IBM Qiskit has added a lot of functionality to support pulse level control, which is really great. But it's still from this paradigm where you're thinking about an instruction set and gates, sometimes some details such as the sampling rate of the hardware propagate up to the higher levels. So what we wanted to do is we wanted to make something that would allow us to really easily express the experiments that we needed to do. And I think the best example to show for this is the Chevron experiment. This is some data we took using this framework a few months ago. It's a very simple experiment that can be used to see if your flux pulses are working all right, and it can be used to then measure an avoided crossing between two qubits. Based on the shape of this interference pattern, you can see how well a job you did with correcting these effects. But what's key here is that we want to mix, on the one hand, purely gate-level circuits. We want to use the high-level abstraction there. And then put something on the pulse level in there and have really fine control about the timing of the pulse. We want to keep, for instance, the separation between the micro-F pulses always constant, independent of the pulse we have in the middle. And then we want to vary the amplitude and the duration. We want to be able to do this not just for a square pulse, but for pretty arbitrary things. And to do this, we're using a pretty standard layering structure. You have the quantum circuit layer with the quantum device layer with configurations that go into that. I think that's also a very relevant part, is how we manage all these parameters, especially once you go down to hardware, because that's kind of to meet what's happening in a lab. And most of the open source framework focused on quantum computing, they tend to hide that information. Or at least force you to make your own backend, and that's kind of what we try to do here. So how does it work? How can we make that work? So everyone's familiar with the quantum circuit layer, but I think one thing to realize that the only thing that matters there is the order of the operations. And things we're adding are typically gates, measurement, and action in qubits. But if we're talking about this quantum device layer, as we call it, we find that the timing is relevant. And we're no longer talking about gates and measurement, we're talking about pulses and acquisition protocols. There's a subtle difference why we chose that name. But these are acting then on these signals should be applied to a certain location on the device. We call these ports, and the frequency denoted by a clock because it also allows us to specify phase information. The realization that we had was that actually there are different representations of the same operation. And if you specify timing, you're also specifying the order. So that means that we can have a layer where we're just adding operations to it. And then as a compilation step, make sure that it all has a valid representation at this lower level. And this is what comes together in the schedule. So now I want to talk a bit more about, now that we have created this, what can we do with this? And I mentioned earlier that there was a strong need for us to have an emulation framework. And the nice thing is, we now have a schedule that specifies exactly at the pulse level what's happening and what kind of signals will be applied at the device. And I think the most important part here is this allows us to not only capture the gate dynamics, but also really silly things like latencies, distortions, all the hardware corrections that we never talk about when we're talking about quantum circuits. I'm calling this an emulator, not a simulator, even though it actually is a very powerful simulator as well. But that's because the goal for us is not to accurately simulate the physics, but the goal for us is to qualitatively emulate all the behaviors that we're seeing. So for some kind of experiments, we manually say, well, we can skip this one step or we can skip this other step. So on the bottom part of this, we have a mock device. This is something that is explicitly hidden from the user, but it essentially contains our Hamiltonian parameters, our coherence times, these kind of things. And they go into a Hamiltonian model. The blue boxes are external libraries we use here. We use SC Qubits. I think most people here are familiar with that. And then we put that together into a custom Lindblad equation solver. The scheduled data structure has all the operations separate from the schedulable. So if we're doing, for example, something like randomized benchmarking, we're not simulating tens of thousands of operations, but we're only simulating the primitives in Lindblad. So that saves us a bit. Goes together into quantum sim, density matrix-based simulator that was developed several years ago in Delft. And the advantage of this tool is that not only is it a density matrix-based simulator, meaning that it's not limited to pure states, but it also allows us to deal with higher energy levels. And that gives us, then, from that we get the populations. Then we have a custom readout model. We don't bother simulating the full dynamics here, but it's a very crude model based on dispersive shifts. And we're recently also adding power dependence and decoherence effect to it. But that's enough to get us measured signals out, voltages. We can also add, at a later point, it's not there, but we could add a crosstalk model there. So the idea here is to have everything qualitatively reproduce the same thing. The power of that is that we can now execute the identical code that we run on the real setup also in our emulator. What you see here is I explicitly put here the example of a spectroscopy measurement because that's something we typically don't simulate. There's another example I'm not showing where we can really see sort of how a square pulse. You also see the sort of the effects of the Fourier transform in the spectrum we're seeing. Like you can really see those details of the timing back in the spectra you measure. This all comes together in our Superconducting qubit tools, where we also put tutorials on how to then tune up the qubits. Now, so far I've only talked about software. I know I'm running a little bit short on time, so I'm going to speed up a little bit. But the need for us is to make hardware systems that can do this. So one thing we did is we partnered with other companies in the Dutch ecosystem. And we said, okay, well, if we take all our products and put it together, we have ourselves a full stack quantum computer. The first one was 2021. In 3 months, we put everything together from scratch, nothing. We built a full stack quantum computer. We were responsible for the system integration and for the operating the lab and tuning everything up. This is just basic experiments. I think most people know about these things. But here we're showing that we went to full coherent control of the single qubits. This year we did a follow-up project. You already saw one of the data sets from there. We did here we have lots of custom developments, new chips by Quantware, custom shielding by Demcon, cables from Delft Circuits, electronics from Qblocks. But I think one of the coolest things here is that we ran a world's first application of a variational quantum algorithm developed by Q & Co. And yeah, we ran a 3-qubit algorithm. I think that's pretty cool. So my summary conclusion is that establishing a fast feedback cycle is key to developing better quantum chips. You need different tools depending on what you want to do. And we built a quantum computer. Thank you. Oh, and by the way, we are hiring like everyone else.
Okay, so thank you. We have a few minutes for questions. Yes, over there in the back.
Thanks for the very nice presentation. 2 quick questions. The first one for the emulator. I assume that one would be really interested in inputting some realistic, let's say, noise sources or errors from the actual experimental device before, diving into emulating it. Does it support this ecosystem like emulator and the real measurement, let's say, software, or how does it work?
Yes, so I think if we're talking about realistic error models, the whole point here was we wanted to really capture the physics and all the qualitative effects. So that means that besides the coherence, we also have emulation of effects like the latencies, the Readout model, give you a feeling of it. For instance, if we would move the flux bias of a qubit, we would also see the Readout was calibrated not being valid anymore. So you can really capture all the dependencies. If something bad happens here, can our automated protocols recover from that? So all these things are captured. Naturally, we pick physically relevant parameters, and we can do that because we're also using the same tools in our lab. So really, because we're using the same tools in both settings, I can say that the matching is very, very well. Yeah.
Okay, and another very quick question. I'm a silicon spin qubit guy, so I'm interested how compatible is your software for other, non-superconducting quantum computing platforms?
That's a very good question. So I think the high-level protocols, things like the randomized benchmarking, gates, tomography, everything at the circuit layer is absolutely compatible. The framework's designed to also be compatible with different backends. So we're also doing projects with NV centers. I show now Transmon work, but we've also worked with Fluxonium qubits. Spin qubit is something we have a history in before we started the company. So I'd be very interested in having a talk with you. But I think also one thing that we should be very honest about is that for every kind of qubit, you need to do the low-level stuff. You need to do it again. Like the framework is designed to work, but the implementation, of course, would be different. But let's have a chat after the meeting. Yeah.
Okay, so I think we're already a few minutes into the coffee break. So thank you very much again.
Just I'm the guy for the organizational announcements again. We are now heading into the coffee break, and we continue here at 10:40. So we have like half an hour or 32 minutes for the coffee break. Please enjoy the last coffee break of the conference and make last new connections, and then be here at 10:40 again. Thank you. I have the picture.
All right, folks, get ready for the last scientific session. We have Juha Hassel, our head of engineering from IQM, to chair the session. So Juha, please come.
Thanks, Mikko. Great to be here. Great to see you still at this time of the conference. Last session, design and modeling. Great to see you in such great numbers. So let's start. Our first speaker is Alexandru Petrescu from École de Mines, France, and his topic is readout problem in circuit QED. So please.
Okay, so thank you very much. So I'd like to begin by thanking you for the invitation. This is a great conference, and I've been learning a lot. So today I'll tell you about this problem with dispersive readout in circuit QED, but first I'd like to acknowledge people I've been working on this problem with. And these are mostly people from Princeton, especially Moin Malika-Clark, and then from Sherbrooke, Joachim and Ross. And the numerical results you'll be seeing are due to a very nice collaboration with Sandbox at Alphabet, which is a Google company. So I'll begin by giving you a very brief overview of dispersive readout for those of you who are not so familiar with it. So the point here is that readout remains one of the most important problems in the field, especially as we're trying to make readout faster and higher fidelity. In the standard scheme for dispersive readout, you would couple the qubit to a resonator via this capacitive coupling, and as in the scheme of the circuit that I'm drawing here, I'll be mostly focusing on transmon qubits, so weakly anharmonic qubits for this talk. And then if you make a Jaynes-Cummings kind of approximation to the full circuit model, then you have this Hamiltonian here, which with each of the three terms being the resonator, the qubit, and then the capacitive coupling. And then typically what we do, we manipulate this Hamiltonian, we perform a unitary, and we go into this dispersive frame. And in the dispersive Hamiltonian, you have now this quantum non-demolition coupling between the qubit and the resonator. And this is what allows us to essentially read out the qubit, because we have a qubit state-dependent frequency pool of the resonator frequency. And therefore, when you probe the resonator with a monochromatic microwave tone, it will respond differently based on the expectation value of this operator sigma z here. And essentially, what gives you the separation between these pointer states in the IQ plane is given by it will essentially be given by this dispersive shift, and this dispersive shift has to be, in a sense, it has to have certain relationships to the kappa of the resonator. But there is a problem with this kind of standard scheme for readout. So your goal is to do this fast and high fidelity. So essentially, the dispersive theory will tell you that you want to increase the photon number in order to get a better separation of the pointer states. But in fact, as experiments show us, in particular here you have a plot from the group at ETH, readout fidelity almost always decreases after some photon number that you put in the readout resonator. And in addition to that, the T1 of the qubit, so its coherence actually drops also as a function of the photon number in the resonator. So both of these are problems that we're trying to address. So there have been multiple theory attempts to understand this kind of behavior. And at low photon number, you can do some kind of perturbation theory. And originally, based on that Jaynes-Cummings Hamiltonian perturbation theory that was favored was this dress-dephasing theory. You can ask me questions about it if you want to hear more details. There's also a theory of stimulated emission, also perturbative, and this will be the first topic today. Essentially, this is a game of non-rotating wave approximation terms in the Hamiltonian, and also of resonances happening in the spectrum of the driven system. I'd like to stress here that because the drive is nearly resonant with the cavity, essentially these problems are very hard both for perturbation theory and for numerical simulations. In particular, simulations are challenging because they require very many states in the Hilbert space. And this will be the second topic. All right, so I'll begin with basically an analytical approach to this problem, and I think by seeing its successes and failures, this will serve more or less as a motivation to the numerical analysis that I will tell you about in the second part of the talk. So here we're just considering this minimal circuit model with 2 degrees of freedom, where you have in blue the resonator and then in green the transmon qubit. And we're thinking about Purcell physics. So the resonator itself is coupled to the outside world, and we're driving the resonator. And at the same time, you can have losses through this very same resonator. So the qubit can only decay through the resonator. It's Purcell physics. And the kind of experiment we're envisioning is you kind of excite the qubit with a pi pulse, and then you keep you fill up your resonator with a steady-state population n bar, and you can do so because your resonator relaxation time is much shorter than the T1 of the qubit. And while the resonator is filled up with this n bar, your qubit is relaxing. So you perform a T1 experiment, but you have a population in the cavity. And then you perform the measurement at some point after a variable amount of time. And this is your typical T1 measurement. And the way we're modeling this system is using a bosonic theory. So you might argue that this is not necessarily the best theory, but for transmon qubits, which are weakly anharmonic, bosons are fine as long as you're not affected by quantum phase slip physics. And we go to a normal mode basis. So this system Hamiltonian here has already seen some transformations. First, we've gone to normal modes. So in this case, the qubit and cavity normal modes here in green and in blue, respectively, are decoupled at the linear level, so you no longer have this capacitive coupling between them. And all the remaining coupling is now at the level of the nonlinearity. In addition to that, we have displaced. And we have done so in order to obtain this kind of attractive 5/4 interaction in the theory. And now we can do a perturbation theory because we have the coupling strength here, which is essentially the signed anharmonicity in the problem. And at the same time, we have the drive strength eta here, which is proportional to the square root of the mean photon number. All right, so essentially we will be doing a perturbation theory in both the weak anharmonicity of the transmon and the drive power. And maybe the main message about these kinds of perturbative approaches is that if you only looked at the RWA Hamiltonian that results from this kind of problem, and you just looked at your Kerr nonlinear oscillator with a cross curve between the transmon qubit and the resonator, you would never get any corrections to the relaxation rates that depend on drive. Essentially, that kind of theory will just behave like a harmonic oscillator. As you drive harder, you cannot change its relaxation rate. However, counter-rotating terms in the theory will actually dress the rates, and in particular, stimulated emission turns out to be very important in the readout regime. So the workhorse in these kinds of approaches is some kind of perturbation theory, and what we used was time-dependent Schrieffer-Wolff perturbation theory. So the way you can think of it, you have this Floquet Hamiltonian here, which is just the time-dependent Hamiltonian plus the energy operator, and you want to perform some time-dependent unitary transformation on it in order to simplify its form, in order to essentially make it more block diagonal from an original form, which is block off-diagonal. So you can think of the off-diagonal blocks as essentially being the counter-rotating terms in the problem. And then you can do this kind of approach iteratively, like, for example, using a BCH lemma type approach. So it's a perturbation theory that you can recursively apply. And you get a target effective theory, which is essentially more diagonal. You stop at some point where your precision is good enough. And I just want to stress that this is actually not foreign. We have seen this over and over. For example, the dispersive Hamiltonian is such a Hamiltonian. And also the black box quantization Hamiltonian, for those of you who are familiar with it, is also such a perturbatively obtained Hamiltonian. But what's important to note is that whenever you do something to the Hamiltonian, you actually have to also wonder what happens to the relaxation channels of that specific system when it's coupled to a bath. So in particular, if you consider the bath coupling, the typical exercise that we do, and this is a more technical slide, is that we have to take the system bath coupling and write it in the interaction picture with respect to the system Hamiltonian in order to identify those transitions in the system spectrum that are prompted by that coupling, by the operator that is coupled to the bath. And in fact, the Schrieffer-Wolff procedure allows us to perform, to write down essentially an approximate form of the interaction picture operator. And what this gives us is essentially will give us a sum of collapse operators with phase factors times the Bath operator. So for those of you who are familiar with a standard derivation, this is exactly what you get in a standard derivation of a master equation. And then upon performing the Born, Markov, and secular approximations, we arrive at a Lindblad form for the master equation. And here you have a sum of dissipators, and each of these dissipators has a collapse operator. Each collapse operator corresponds to a certain frequency, and here you have the Bath spectral function taken at that particular frequency. So in particular, the two most important dissipators that you have for this Readout Hamiltonian, for the Readout problem, are these two. And here I'm just graying out all of the unnecessary details and trying to show you just the operator structure that you have in these collapse operators. So you have a collapse operator at the frequency of the qubit, and this collapse operator contains a static Purcell, which comes from simply the hybridization of the qubit with its resonator. In addition to that, you have a nonlinear correction to the Purcell effect, which is proportional to the nonlinearity, and it turns out to be decreasing. So we know actually that the Purcell effect with drive should be decreasing. And then in addition to that, we have the stimulated emission term, which you see as some kind of correlated decay where you have two photons, one escaping the qubit and one escaping the cavity. And this is proportional to the strength of the drive eta, the coherent term, which is also the square root of n bar. And it will turn out to give us linear corrections to rates which come from stimulated emission. I'd like to point out here this denominator, which is quite problematic if you look at it carefully, because this is a denominator which is small. The drive frequency is very near the cavity frequency in Readout. So essentially, this predicts that as you move the drive frequency away from the cavity normal mode, you should see some kind of algebraic decay of this rate. But it also predicts that as you approach the Readout regime, this perturbation theory should break down, at least at large enough n bar. And of course, you also get this cavity decay, and the cavity decay is what you would expect. In addition to that, you get some qubit dephasing induced by the cavity. And I would like to point out that there are many other dissipators, some 36 of them at different frequencies that you can derive from this approach, but these are the dominant ones, the most important ones that give contributions to T1. So this is the kind of prediction that you would get from such a theory. What we're seeing is that if you just had a Kerr theory, and if you looked at the change in the relaxation rate of the qubit versus the drive power, you should see absolutely no change. If you just had a Kerr Hamiltonian with the dissipator of the A operator corresponding to the cavity. In addition to that, if you consider only those nonlinear corrections to the Purcell effect, you should see that the Purcell effect decreases. So you should see a slight increase in the T1 of the qubit as you increase the drive. But most importantly, if you consider the stimulated emission terms, or essentially all of the terms in the effective master equation, you should see large increases which go linearly with the n bar of the relaxation rate. And already coming back to that problem that I pointed out, you see that these corrections actually turn out to be quite large even at pretty small n bars, as predicted by this theory. So I would like to state that this is one of the failures of the theory, but one of the successes of the theory is that it indicates the right terms or the right operators that are at play in order to enhance the T1 enhance the qubit relaxation rate. And in particular, there's a prediction here that at least at sufficiently small n bar, you should have a linear increase, and monotonically linear increase in the rates. Good, so what can we do about this? How can we improve on these analytical results? So our first thought was that, in fact, you should actually try to do some kind of full numerical simulations in order to capture these effects better. So for that, this was a collaboration with Sandbox at Alphabet. We kind of had an intuition that we need very large Hilbert spaces, because when you have nearly resonant drives, even though the resonator has some dissipation, you typically fill up the resonator very quickly, and you want to avoid any kind of Hilbert space boundary effects. So in fact, for the results that I'm going to show you here, we needed sometimes Hilbert space sizes up to 2 to the 15 in order to converge our results. What we were interested in studying were essentially not just the Readout regime and what happens to the low energy manifold, so just the 0 and 1 states of the qubit, but also transitions out of the cosine well of the the transmon qubits. So essentially probing this so-called ionization physics of the transmon, where you're exciting the qubit out of its bound states in the well and basically transferring it into these Bloch-like waves of the coming from this Hamiltonian. So essentially, we considered no longer a bosonic approximation to this Hamiltonian, but we considered the full cosine potential for the qubit, which is capacitively coupled to the resonator. And then here is a notation that we will be using on and on in the next slides. We essentially take the transmon and we diagonalize it, and we work in the energy eigenbasis of the transmon for this diagonalization, and we denote the eigenstates of the transmon qubit by I. And what's important to note is that the states outside of this transmon well outside are charge-like eigenstates. So they are eigenstates of this operator n sub t for I approximately greater than 7 in the regime of Vj over C of about 50, which is a typical regime for transmon qubits. So what we did, we actually simulated the dynamics. We simulated the master equation. And as opposed to the approach that I showed you earlier, we considered a much simpler, if you want, or much stricter assumptions on the spectral function of the bath. In particular, we assumed a flat spectrum. And if you assume a flat spectrum under a Born-Markov secular approximations, then the master equation takes a much simpler form, where you just have this dissipator of the photon annihilation operator on the cavity. Then we took a set of very typical parameters for this circuit QED Hamiltonian. And in our time dynamics simulations, we considered two very simple observables. We considered the photon number in the resonator, which is this operator here. And we considered its expectation value as a function of time, extracted from the density matrix. And at the same time, the transmon excitation number. So if you think this is the best correspondent to the photon number in the transmon when you have the full nonlinear spectrum of the transmon. And we did something very simple and intuitive. We started the system in either the G or the E state of the transmon, cross product with the identity on the in the vacuum of the cavity, and then we just did the simulation in order to monitor these two populations as a function of time. Okay, so basically for the results, what we see is that essentially if you start in the ground state of the system, you will get essentially the population of the transmon will be increasing, but not too much. You will not get any ionization. In particular, in blue here, you're seeing the populations of each of the states of the transmon, and you see that there's barely any occupation. So in particular, you will be somewhere low in the transmon well. But if you start in the excited state, you will see that actually there's a threshold as a function of time where you will actually get a large excitation into the states outside of the well. And in particular, if we monitor the resonator population, we see that there's a very interesting neat correspondence to the resonator population. By tracing out the resonator and calculating the purity of the transmon reduced density matrix, we see that this ionization threshold is associated with a specific drop in purity. And this drop in purity happens at a very definite number of photons in the resonator. So in particular, what we notice is that if we plot the resonator population versus the transmon population, there's some kind of data collapse. So there's some kind of universal behavior where you see the ionization threshold occur at very specific resonator populations corresponding to about 112 photons when you start in the ground state and about just 40-something photons when you start in the excited state. Just about how much time is left? 2 minutes left. Okay. Good. So basically, I'm just going to make a point here that these ionization thresholds are associated to instabilities in the spectrum of the system. We have a way to track all the states in the spectrum. And we note that there are certain resonances between the low-lying states in the spectrum and other states above, between, say, 5 and 7. And these states actually give us the possibility to tunnel into outside of the transmon well. And essentially, we can immediately trace in the semi-classical analysis that we do based on the undriven spectrum the positions of these instabilities, and we can understand the threshold of ionization. And I'd like to mention that these thresholds, if you go to the parameters, for example, of the ETH experiments, these thresholds are actually very near what we expect from the experiment, and we have a more a precise analysis based on Floquet, which actually allows us to pinpoint that exactly at around 2 photons, you should have reductions in fidelity due to the strong hybridization of states in the transmon low-lying spectrum with higher states, which we understand now to be chaotic. And with this, I'd like to thank you for your attention.
Thanks. Time for a couple of questions.
Yeah, thank you very much for the nice talk. So can you say how you deal with charge dispersion in these devices when you consider the high levels of the transmon?
Yeah, that's a wonderful question. So there was not enough time to talk about this, but essentially charge dispersion effects become very important as soon as you turn on the drive. In particular, the bandwidth of the 0 to 1 transition gets severely enhanced by the presence of these chaotic levels above the qubit manifold. And in general, we actually keep track of charge dispersion. We take a full Hamiltonian, and we also see that the effects are very sensitive on the value of the background charge. So the positions of these spurious resonances that affect fidelity are dependent on whether you take NG equals 0 or 0.25, etc.
Okay, if no further questions, let's thank the speaker again. And we can proceed for the next talk, which will be Ahmed Kenawy from Forschungszentrum Jülich. And the topic is correctly account for time-varying fluxes in superconducting circuits. So please.
Thanks for the introduction. I'd also like to thank the organizers for the very nice conference. I think we all enjoyed ourselves, and we're kind of looking forward to next year's event, hopefully. Also, I'd like to thank everyone who stayed till the end of the conference. I know it's a Sunday and people want to leave, but yeah, thanks. It's nice to have an audience. So in this talk, I would like to discuss how to account for time-varying fluxes in superconducting circuits. But before I start, I would like to acknowledge that the first half of this, or the work done in the first half of this talk was actually carried out by Roman Riwar and David DeVincenzo in Jülich before I joined the team. And the main results of this half is in this NPJ quantum info paper. The rest of the results are in this PRB paper. So as you all know and have seen in the past 2 days, superconducting circuits are currently a very promising platform for creating quantum bits or scalable quantum computers or even quantum hardware in general. And one of the cornerstones of this field is circuit quantization. Circuit quantization simply allows us to construct a Hamiltonian that describes the quantum mechanical behavior of a given electrical circuit. And of course, the success and practicality of circuit quantization is evident by the huge zoo of superconducting devices that we have. So there's no denying that. But one limitation that I want to focus on in this talk is that standard circuit quantization generally assumes a time-independent magnetic flux. But of course, time dependence arises naturally when you would like to intentionally modulate the magnetic flux or when you consider flux noise. So the problem generally is that the standard form of circuit quantization does not properly account for time-dependent electromagnetic fields. And the origin of this issue can be traced back to basic physics, to gauge freedom in electromagnetic fields. So as you all know, we can represent the two physical fields, the magnetic field and the electric field, using the two potentials, the scalar potential and the vector potential. And of course, gauge freedom implies that we have different sets of these two potentials that corresponds to the same physical fields. Importantly, it is these two gauge-dependent potentials that goes into the circuit Hamiltonian. And this simply means that we have an entire family of Hamiltonians that correspond to the same physical circuits. And all these Hamiltonians are related by unitary transformation U. So somehow there's a direct correspondence between gauge transformations and between a change of basis using a unitary transformation. And that's all fine as long as you have time-independent fields. But once you have a time-dependent field, the situation is more complex, and this direct correspondence fails because now the unitary transformation itself becomes time-dependent. So when you change basis from one basis to the other, you have an additional term in the Schrödinger equation that depends on the time derivative of this unitary transformation. To give an example, if you have a time-dependent magnetic field, then this U dot term will be proportional to the time derivative of the flux. So this will be an electromotive force term. And this term can really change the dynamics of the circuit, but until recently, its importance has been neglected in literature. So to give you a more concrete example, let's consider that we have an asymmetric DC squid, an example we're all familiar with. So here a squid consists of two Josephson junctions. It's asymmetric, so the two Josephson energies are not the same. And we assume that we have a magnetic flux bias phi. Now we would like to write down the Hamiltonian of the circuit. So we follow the standard quantization procedure. And what we do is essentially we choose a spanning tree that goes from the ground to every active node we have. In this case, we only have one node, so that's easy. And then by convention, we assign the external flux to the closure branch. And this leads to this kind of Hamiltonian. So we have the first term is like a kinetic energy or charging energy term. Then you have two inductive terms, and you assign the flux here, so phi, the external flux bias, to the left Josephson junction. That's one way to do it. Alternatively, we can choose our spanning tree to be the left branch, and then we assign the external flux to the right branch, and this leads to this kind of Hamiltonian. So it's more or less identical, but now the external flux is here. And of course, these two Hamiltonians are related by this unitary transformation. So the gauge freedom I was talking about corresponds to the question, to which of the two Josephson junctions do we give the external flux, to the right one or to the left one? Or in a more generic term, if we have an arbitrary circuit, the question would be, to which of the potential energy terms do we have to assign the external flux? So to give you another example, if you have a flux qubit, the question would be, do we give the external flux bias to the Josephson junction or to the inductance? And that's fine. We can do whatever we want. This question is quite irrelevant as long as the flux is time independent. But if the flux is time dependent, we start to run into problems. To see what kind of problems, let's assume that this flux fluctuates around a mean value, and we try to calculate the relaxation rate of the qubit. Using Fermi's golden rule, we see that the rate depends on the derivative of the Hamiltonian with respect to the flux. So if we assign the flux to the left junction, then the rate will be proportional to the Josephson energy of the left junction. If we assign it to the right junction, the rate will be proportional to the Josephson energy of the right junction. And because this device is asymmetric, we arrive at a paradoxical conclusion that the phasing rate seemingly depends on our choice of the spanning tree. And in fact, the situation is more complex because there's more ways to divide the flux. For instance, I can give a fraction alpha to the right junction and the remaining fraction 1 minus alpha to the left junction. So in a way, there is infinite ways to divide the flux between the two Josephson junctions. And this, again, leads to an entire family of Hamiltonians that we can relate by a unitary transformation U. So the solution to this inconsistency was proposed by Yu et al. From Jens Koch group. And they say that the correct time-dependent Hamiltonian, which they call the irrotational Hamiltonian, can be obtained by imposing a constraint on the parameter alpha. And for this simple circuit we have, this constraint translates into dividing the flux based on the ratio of the two junction capacitances. So if you have two junctions and they have the same capacitance, then basically you give half of the external flux to the right junction and the remaining half to the left junction. And if you're interested in this, there actually has been a paper on the archive, I think about a week or two ago from Princeton that verifies this idea experimentally. You can find it in this green archive link. I think they work on the fluxonium qubit and they verify this idea of flux distribution. But one limitation here that I want to focus on is that we assume that we can assign individual capacitances to each junction. And this is quite an assumption, as I will show later, which means that this proposal only works in the limited setting of lumped element model and cannot really tackle continuous device geometries or arbitrary profiles of the external magnetic field, which is what we intend to solve in this talk. So what we do is we reconsider the squid example, but in a kind of realistic device geometry. So the squid arbitrarily would consist of two superconducting lumps. One of them you can call an island, and the other you ground. And these two lumps are connected via two junctions here. And of course, you still have your time-dependent magnetic field enclosed in this hole, and you have an electric field between the two lumps. And our goal is to generalize this idea of the rotational Hamiltonian into an actual gauge choice in which we solve the electromagnetic problem. And to do so, we divide the electric field into two contributions. One of them takes care of the charge separation between the two metals or the two superconductors. And the other contribution takes care of the time-dependent, the electric field induced due to the time-dependent magnetic field. So this is kind of the electromotive force term. And importantly, we include this second contribution into the irrotational vector potential, such that in this way, the irrotational vector potential, or we call it irrotational analogous to the irrotational Hamiltonian, takes care of all the effects related to the electromotive force term. And now, having calculated this irrotational vector potential, we can simply integrate it along whatever path we want to obtain the phase drop. So to obtain the phase drop along the two junctions, we simply integrate the vector potential here and the vector potential there. And as long as we assume the magnetic field is concentrated within this hole, we can reproduce the results of the of Yu et al., the results of the lumped element model. But of course, our proposal is more generic in the sense that we can have arbitrary profiles of the field. So we can now even assume that the field goes outside the hole, or it can even fall on the superconductor itself or on the Josephson junction. And in this case, of course, these cases cannot be handled by the previous model. But now if we insist on going into the lumped element approach and assign individual capacitances to each junction, we can see that these capacitances can actually be negative time dependent or even momentarily singular. And the whole idea here is that for a realistic device, what you have is a total capacitance between the two lumps. But really, the notion of individual junction capacitance is not well defined, at least for our arbitrary geometry. And of course, these negative time-dependent capacitances can have different consequences. But to name a few, they can, for instance, lead to a strong enhancement of the qubit relaxation rate, much higher than the lumped element approach would predict. And secondly, you see that the Hamiltonian is now a function of two time-dependent parameters here, C left and C right, which means that you have a two-dimensional parameter space, so you can acquire periphases by moving in this space. Of course, if you're interested, you can find more consequences here in this reference. But having developed this recipe to obtain the correct time-dependent Hamiltonian, I would like to apply it in a different context, namely Majorana quantum circuits. So for this, we consider two topological superconductors coupled weakly, and we model them here as two Kitaev chains placed on top of S-wave superconductors. And you can see by this notation here that these two superconductors are connected at the far end to form a loop, and this loop is threaded by an external magnetic flux. And this leads to a phase difference here, phi. So as you may know, that the low energy physics of this model is governed by the fractional Josephson effect, which simply couples the Majoranas of the left and right chains, represented by these two operators here. And it's a fractional Josephson effect, so you see that you have phi over 2, and this simply means that the weak link allows tunneling of single electrons and not Cooper pairs. Of course, this description is correct as long as we have a time-independent magnetic field. But if we have a time-dependent field, then we have to follow our recipe. And the first step was basically to calculate the irrotational vector potential. And in this case, it takes the form of an electric field between two coplanar capacitors. You can think about it this way. And using this irrotational vector potential, you can simply integrate from the relevant superconductor to the site in question to obtain the phase drop across each side of the chain. So this is an example of the phase drop profile over the entire model. So D here is the separation between the two superconductors. And you immediately see that the phase drop not only takes place across the weak link, but it's rather distributed along the entire system. And this distribution, of course, depends on the profile of the magnetic field and the dimensions of the system. And it decays like 1 over distance from the edge of the superconductor here. But of course, this is a little bit idealistic in the sense that we assume that you can align the edge of the chain or the nanowire exactly with the superconductor. So for a more realistic configuration where, for instance, the chain can extend a little bit into the space between the two superconductors, you see that the phase drop along the chains is even higher. And less phase drop actually takes place across the weak link, which is what's usually assumed in literature. But in general, the key message here is that the phase drop not only takes place across the weak link, but rather has a distribution over the sides of the chain. So now what we've done is we've calculated the irrotational vector potential. And based on this, we've integrated it and calculated side phases. And using these phases, we can calculate the correct time-dependent Hamiltonian. But of course, we can still choose to work on the convenient basis of including the entire phase drop here by doing another unitary transformation. But now we have an additional term that we have to take care of. So now we know we're not missing anything. So you can still work in whatever convenient basis you want, but now you can keep track of what terms are missing. And if we do a Schrieffer-Wolff transformation, as a previous presenter was discussing, we can derive the low energy physics of this model, and we see that there is a correction term to the fractional Josephson effect. And this correction term depends obviously on the time derivative of the flux, so it's an electromotive force term, but it also depends on a new parameter lambda. And this parameter is, of course, a function of the geometry of the system and a function of the profile of the external magnetic field. And importantly, it's only 0 if you have a perfectly symmetric system. Once you have some sort of asymmetry, whether due to different parameters of the two chains or whether it is due to the profile of the field or even simply an asymmetric placement of the weak link, which is more realistic, then this parameter can be significant and actually as large as the Josephson energy itself. So it can really change the behavior of the system. Now, having developed this effective Hamiltonian for a fractional Josephson effect, we can use it to study the behavior of a topological Josephson junction in an open circuit geometry. So for this, we simply can cut the superconductor loop. Now we have two lumps. One of them we ground, and the other is connected to is controlled by a gate voltage. And here I represent the chains or the nanowires in blue and the superconductor in gray. And of course, here the dynamics will be depending on charging and discharging of a capacitor rather than the time-dependent field. And interestingly, there's two ways to think about this circuit. The first way, we can assume that the nanowire or the chains themselves can host a charge. And in this case, they're kind of irrelevant to the overall capacitance between the two superconductors or between the two metals. And this choice in the closed loop corresponds to saying that the phase drop takes place across the chains themselves. So basically, lambda will not be equal to 0. The other way to think about this model is to assume that chains are part of the bulk superconductor. And in this case, they can perfectly screen the electric field, and they cannot host charge. So this is equivalent to saying that the phase drop takes place exclusively along the weak link. So basically, lambda here is 0. And to compare these two models, we can write down the Lagrangian, and we see that the Lagrangian of the left circuit has an additional term that, again, depends on the time derivative of the flux and depends on lambda. And we can now follow the standard procedure that you all know. We calculate the conjugate momenta and then do the Legendre transform to write down the two Hamiltonians. And we would see that the only difference between the two Hamiltonians is that the charge operator of this circuit is shifted by the amount of charge induced on the chains. And this is dependent on the parameter lambda. And of course, this can lead to several measurable effects. For instance, if we calculate the fluctuations of the number of Cooper pairs on this island, we will see different behaviors for the two circuits. So here I show the charge fluctuations as the function of the ratio between the Josephson energy to the charging energy for the ground and the first excited state. And for a large ratio here, you see that the two circuits behave similarly, but as the charging energy increases, they behave quite differently. And ultimately, for a very large charging energy, one of them predicts 0 fluctuations, but the other predicts finite fluctuations that is proportional to lambda, which shows that we need this correct description for the fractional Josephson effect. So in conclusion, I've proposed a recipe to construct the correct time-dependent Hamiltonian for a continuous device geometry and arbitrary profiles of the external magnetic field. And we've used this recipe to describe the topological Josephson junction, and we've showed a correction term that depends on the geometry of the system. And finally, we've seen that this correction term in an open circuit geometry can lead to different predictions, such as non-zero fluctuations, even in the limit of large charging energy. At the end, I would like to thank you for listening and share my email in case you want to get in touch with me. Thanks.
Thank you. Time for questions.
Thank you. Very insightful. So, in classical circuit analysis with time-varying magnetic fields, I think you get around this problem by using loop currents instead of node voltages. So is this the same idea in a quantum context, or is this?
In classical circuit analysis?
Yeah, so you can consider node voltages, but you can also write loop currents. So it's kind of dual.
I'm not aware of this, to be honest, for classical physics. But the problem is that when you do a unitary transformation, you go to different bases, which is fine, but you still, if you want to describe your dynamics using Schrödinger equation, there will be an additional term here, right? And because there's an additional term, and we're not really deriving our Hamiltonian from the ground up, there's no way to know which is the correct Hamiltonian. So what you et al. Proposed is that the correct Hamiltonian would not have any linear terms in the charge. So the correct Hamiltonian would not have a phi dot n term. And once you know that, you can still do any transformation to go to whatever basis you want. I hope this answers the question.
Probably. Thank you.
Further questions? If not, one there.
This is it's kind of a tricky question. So, is there any way you could cancel some of the effects of the drive on flux by a drive on the gate, directly a charge drive? Since you seem to be having this alchemy of moving them back to the charge.
Probably yes, but to be honest, I haven't investigated this. But
okay, so there's no go theorem that.
Yeah, there's nothing like straightforward. Yeah.
Okay, thanks. Let's thank the speaker again. And our next speaker is Thomas Ramos from the Institute of Fundamental Physics within the Spanish National Research Council. And the topic of the talk is amplification via a topological Josephson junction array. So please.
Thank you very much for the nice introduction. And I also want to thank the organizers for the opportunity to speak here to you. But today I will present to you a new proposal for building a truly directional Josephson traveling wave parametric amplifier, where the directionality comes from the non-Hermitian topological properties of the device. Well, we have already seen many talks in the conference talking about the importance of amplifying microwave signals coming from superconducting quantum circuits and having efficient amplifiers for that. And in every quantum amplification process, you will have some gain G and also some added noise N, always by the laws of quantum mechanics. And therefore, we typically require isolators in order to protect the quantum system from the noise coming from the amplifier. One of the most advanced amplifiers so far available are Josephson traveling wave parametric amplifiers, which are built of a carefully engineered array of Josephson junctions. And these devices work very well. They have shown nice figures of merit like large gain, near quantum limited noise, and bandwidth on the order of gigahertz. But still, it would be very nice to have an upgrade to them and make them non-reciprocal, as we have seen already yesterday in some talks. In this case, if you send a signal on the first side, this will be unidirectionally amplified from left to right until the end without any reflections, and therefore without any backward noise going to the quantum system, and therefore we don't require these isolators, and we can scale better the quantum devices. But so far, this device has only been done in a narrowband way, as we have seen yesterday by a talk of one of the speakers, one of these reference. But today I want to show to you that this is possible to do a directional and broadband amplifier using concept of topological amplification, which was developed in these 3 seminal theoretical papers, and using state-of-the-art technology in circuit QED. Okay, this is how it looks, the implementation I want to propose on the right of the screen. On your left, which is, and on the right, I have the equivalent quantum optics model that we implement with this circuit, okay, which will be a weakly anharmonic resonator array. And it has 3 main ingredients, the implementation, which is one is in blue is the Josephson junction array, which is homogeneous, where we have on each side, we have a Josephson junction, which provides self-care couplings, and we also have Josephson junction between the sides here, which provide cross-care couplings between sides. In addition, we have a capacitance that couples sides and gives rise to this linear hopping JA. in addition to this, we have the second ingredient, which is in gray, which is we couple to each of the sites an additional 50 ohm transmission line to provide decay on each of the sites with a decay rate kappa. Okay, and we also these ports will be used to send the signal that we want to amplify and to retrieve the signal when we want to take it out. Okay, and the last ingredient is shown in red, which is a linear array of superconducting resonators. That this will be the key to make this device topological, as I show in the following. Okay, but first, imagine we don't have this linear array, only we have the JJ array, and that we have n independent pumps on each of the sides. Okay, all with the same strength, but with different phase that changes linearly in space from left to right. So first one minus phi, then minus 2 phi until minus n phi. So if we can have this kind of non-local pump on all sides, which is described by this Hamiltonian, we can break time reversal symmetry and make the device topological. Okay, but this may be not so practical in experiment because we need too many pumps. So then that's why we came with the idea to have an auxiliary resonator array where you can pump only on the first side here in B1, and then this array distributes the pump over all the sides on the JJ array automatically. And to make this happen, you need 3 conditions basically, which are shown there. The first condition, you need to drive on resonance and strongly. The second is that the coupling between arrays needs to be weak and off resonant. And the third condition is that we also couple on the last side of the auxiliary array, we couple another transmission line with the decay 2 times the hopping on the auxiliary array to have perfect impedance matching. And if we do that, all photons that enter in the first side of the auxiliary array will propagate to the right and will be perfectly absorbed on the last side without reflection. And if we do that, in steady state, we can build a nearly classical running wave in the auxiliary array, which will have a very well-defined phase, will be this pi over 2. Oh, well, the pointer is not there. But this is a way that we can, in practice, build this non-local pump on the device. And we can use this pump to do 4-way mixing and make an amplifier out of it. Okay? So when we do 4-way mixing, we drive strongly, and we displace all the modes on each side by an amount alpha, and then around it, there will be some quantum fluctuations, delta AJ. Okay? And what is very nice from this implementation is that the same phase phi that comes from the pump provides perfect phase matching along the JJ array, and you don't need to do dispersion engineering, so the array can be completely homogeneous. Okay? Well, we can adiabatically eliminate the auxiliary array, so we can forget about it, and we are left with the dynamics only of the fluctuations of the Jason junction array, which look like that. And for sufficiently strong pump, these dynamics can be linear. Okay, so we have a linear amplifier. And the dynamics is described, and by that formula in the Heisenberg picture, we can see that we still have this local decay kappa on all sides, and we have an effective parametric amplifier Hamiltonian, which is shown on the left of your panel. And it has 2 terms, one proportional to K, the matrix K, which is parametric pumping terms that provide amplification. And the second term are, okay, and inside these parametric pumping terms can be of 2 types. One can be local, which is JS, and also non-local JC, which is proportional to the linearizing the cross-kerr coupling. That's why it's very important to have some cross-kerr coupling. And the other terms are photon-conserving terms, proportional to M, where we can have standard detuning on each side. And also, very importantly, we have complex hopping. Okay? So, and notice that this complex hopping, the phase comes directly from the PAM as well. So it's like having an artificial gauge field for our quantum fluctuations that do not require any type of Floquet engineering or any external magnetic field. So this really comes from the phase of the PAM directly. And the nice thing here is that as a combination of this local decay kappa, the non-local parametric pump GC, and the complex phase in the hopping, we can show that the steady state of this device enters a topological phase, and where all photons propagate from left to right unidirectionally, and they accumulate on the last side exponentially. And this will provide exponential gain for the amplifier, as I show in the following. And to describe this, it's very convenient to write the dynamics in a matrix form and define this non-Hermitian dynamical matrix, which contains all the coherent and incoherent processes in a unified way. Okay, and I will use this matrix to describe the spectral and topological properties of the device. Okay, so and for this, it's important to define the Green's function matrix G, which is nothing more than the inverse of the non-Hermitian dynamical matrix I defined before. So I think I need the water. Thank you. Sorry. Okay, so the Green's function matrix is nothing more than just the inverse of the non-Hermitian matrix. And from this, we can define all amplifier properties of all properties of the amplifier. For instance, the gain of the amplifier or the reverse gain. So the gain, if I send a signal on the first side, and I measure the signal at any other side j, as I shown there, the gain is just given by the square, the modulus square of this Green's function matrix. And if I want to now get what is the gain of a signal propagated in the opposite direction, then it's the same formula, but just I need to reverse the indices of the matrix, okay? So we can see from this that a non-reciprocal amplifier requires to have an asymmetric Green's function matrix, okay? And to show that for in a topological phase, this is indeed the case, that it becomes asymmetric, we use a connection that we developed in our group in these 3 papers between the open quantum system and the amplifier itself and topological band theory, okay? So I don't want to go in theoretical details and technical details. I just want to say that we basically what we do is we take this non-Hermitian matrix, and with this we build an Hermitian matrix. By construction, it's Hermitian, so we can always do that. And this matrix, it's a Hamiltonian, we can diagonalize it, and we can get eigenenergies and eigenvectors, okay? And imagine this is a topological insulator Hamiltonian. For certain parameters, you can find 0 energy modes. So you can see here, this is the eigenenergy as a function of frequency. And for certain frequency bandwidth, we find 0 energies. And this means that there are edge states in the system. And you can say, well, I invented this Hamiltonian, maybe it has nothing to do with the physical system, but actually it has a big consequence, which is that the Green's function of the real system, when this happens, get an exponential dependence in space, as I show here, with this exponent, where the exponent is the localization length of this artificial Hamiltonian that I defined before. Okay, and this has very, very deep consequence on the amplification, because if you replace this exponential dependence on the definition of the gain and reverse gain, you can see that the gain will increase exponentially with system size from left to right, and the reverse gain will exponentially suppress from left to right. And you can see that already with 27 sites, the device can provide 30 dB of amplification and minus 30 dB of reverse attenuation. And this is at resonance, let's say, it's at the frequency of the pump. But what happens if we go away from the frequency of the pump? If we study the bandwidth performance of the device. So here I show the gain as a function of frequency with respect to the pump, the reverse gain, and the added noise of the device for the parameters I showed to you before. And I take parameters that are similar to this paper by Eichler et al. At the group of Andreas Waldach in 2014, to be sure that I take realistic parameters in the calculation. And we can see in the gain plot that we get already 1 gigahertz bandwidth above 20 dB of amplification with a maximum 32 dB for these parameters. And here I take the pump to be at 8 gigahertz, but this can be tunable also by flux if I replace all the JJs by squids, for instance. And reverse gain is maximum minus 30 dB, but can be even lower if you are away from the pump. And added noise is close to the quantum limit. Here I take the convention to the quantum limit at 1. So this means close to the pump is only 0.9 photons above the quantum limit. So this is more or less the nice performance of the device. But there is one caveat that is very important to control the saturation of the device to make this work. Okay, because I said that the gain grows exponentially from left to right very rapidly, but also the occupation of the fluctuations in the device also grow exponentially from left to right. This looks linear, the plot, because I use a logarithmic scale, and the maximum is a 1 because I divide by the average displacement. Okay, and I said before that we need this quantity, this ratio, to be much more than 1 always on all sides to make the device to work linearly, okay, to avoid saturation. And for this, for the parameters I took before, when you need really on the order of 3,000 photons on average on each side of the device to work, and this means on the one side that you require a large pump, so you need minus 50 dBm of pump, which is relatively large, but has been done already in experiment. But on the other side, there is an important limitation, which is that you need to respect the weak flux condition to get a weakly enharmonic Josephson junction array, which is what I show here in the red square. And this mainly says that you will be limited by the size of the effective capacitance in the device, and it's not so practical to have this very large. Okay, so in principle you can say, I can take capacitance infinity, but it's not practical. You get other problems. But fortunately, there is other people already encountered this problem when they studied JPAs, standard JPAs, and in the group of Andreas Baldraff, and also in an experiment more recently in the group of Nicolas Roche. And what you can do to reduce this saturation is to replace every Josephson junction in the array by a sub-array of m other Josephson junctions in series, okay, where the Josephson energy is m times larger than before. So if you do that, everything will be the same, except that the total flux, let's say from one end, when I don't have the pointer, but from one end to the other, will be the same, but on each element will be m times lower. Okay, and this, what it makes the upper limit here in this inequality will be increased by m squared, depending on the number of m that you can build. Okay, and with this we can really control the saturation, and then it's no problem as long as you can build many JJs in series. And we have calculated that you have on the order of 30, which was already implemented in these experiments. You can avoid saturation in the previous, for the parameters I already presented to you. And for 27 sites, which is what I consider in the example, now you require on the order of 2,000 JJs to make this work, which is still reasonable because for standard 2-pass, I think they also can reach on the order of 2,000 sites. Okay. Okay, and this is the last slide. So the last nice property of the topological amplifier I want to comment to you is that it has an intrinsic topological protection against disorder. So I said that the device should be completely homogeneous in principle, but of course, due to fabrication errors, in the JJs mainly, they will get inhomogeneities, okay? But due to this intrinsic chiral symmetry in this Hamiltonian and the gap that we have, the system is robust against disorder in all system parameters, as I show here. Here I show the average gain, reverse gain, and added noise, and I show that for up to at least 10% of disorder in all system parameters, the quantities are almost doesn't change, almost do not change. Okay, so it's very robust against disorder. Well, that was all I wanted to tell to you. So in summary, we think that with this proposal, building a topological Josephson 2-pi is within experimental reach. And the key to make this happen is to couple the JJ array to an auxiliary resonator array, where this provides two things, the phase matching and also an artificial gauge field. It doesn't require any type of forget engineering or reservoir engineering. The figure of merit can be comparable to state-of-the-art 2-pass and could be improved with more optimization. And the array is homogeneous and robust to disorder. And in the outlook, I just want to emphasize the third point, which is that this system is not only interesting from the point of view of applications, but also can be interesting to observe new dissipative steady-state topological phases of matter. And this is what we also study here in this other reference. It's on the archive, where we show different topological phase diagrams that you can see with different winding numbers and that depends on the parameters. So I want to acknowledge my 4 collaborators on this, and I want to thank you very much for your attention.
Thank you. Time for a couple of questions.
Hello, and thanks for a nice talk. Very interesting. I actually have quite a lot of questions. I'll seek you up later. Like I didn't really follow how the curve, like what happened with the curve effect and and wave velocities and stuff. But what I will ask now is if I understood the structure correctly, like you have the pump in a separate line in parallel with with this array. All right. And how what are the wave velocities? Are they the same through this chain? And how?
Yeah, they are the same. But this is by by construction. They become the same. Yeah.
All right. Well,
yeah. So they're in phase. They're in phase.
All right. Thanks.
Yeah.
Yeah, thank you very much for the nice talk. So I'm trying to understand where the topological properties here come in. So you mentioned non-Hermitian topology, but is this here coming from, just the coherent coupling and, and pumps which you have in the Hamiltonian? So is the Hamiltonian topological, or is here the topology coming in due to some dissipative effects?
Yeah, it's a combination of dissipation and coherent interactions. So it's a combination of the local decay and the phase in the hopping, let's say, and the non-local pump. So it's the three.
So if you would switch off the dissipation, the model would not be topological.
No.
Okay.
No, you need decay to exactly, and it needs to be homogeneous. In standard two-pass, typically you have more dissipation, or you have a line only in the first and the last side. But that's why we need to have a transmission line on all sides to get dissipation on all sides, because this is needed for the topological regime to reach the topological regime.
Thank you.
Okay, there's one more.
Hey, thank you for that talk. Do you need this dissipation term to be here? Do you need all these dissipation term to be incoherent with each other, like separate dissipation channel? Like if you imagine coupling everything to a single waveguide, you're going to get some coherent interaction between sites. So do you need separate 50 ohm loads for each of your nodes?
No, maybe you could have a common one, but then you can have, let's say, long-range interaction mediated by this. So I think this doesn't kill the topology. So just will change the phase, probably. So you need to kind of study, it will be you can implement a different model, but probably still this can behave topologically and have amplification. Yes, it's more complicated to calculate, so you have long-range terms. Yeah.
Okay, I think we now need to stop and the discussion can continue. After the talk, I believe the next will be the closing words by Mikko. So let's thank all the speakers once more.
Oops, no. The continuation is there.
Right. We had a very successful conference, first of its kind, and it would not have been possible without you. So here you can see our group photo from yesterday, and this is really the spirit that we want to gather here to. We want to gather to this conference every year from now on, and discuss, have very, very high-level scientific content, like we saw in this conference. Some of the best research groups in the world were giving talks here, and we like to keep the ambition level high and the quality very high, so that it will be a great honor to give a talk here in this conference. But at the same time, it's going to be a lot of work for those who prepare the talks. So again, I'd like to thank especially everybody who has given the talk here, because I know how much work it is to make a great talk. And of course, the posters were also amazing. There were a lot of kind of just latest results given also at the posters, and in addition, they were complementing the talks really well. And also the corridor discussions, I could say that sometimes you didn't want to come actually even to the lecture hall in time, because there were so good discussions going on in the corridors, and that's of course part of the thing, and that's why we also wanted to have not talk after talk after talk after talk, but also give you time to discuss. And I had very useful discussions during the lunch break and during the coffee breaks. And that's what makes the conference a real scientific event to attend on site. And one of the things I actually liked is that also all the stands, you can see the IBM stand, for example, there, they were very close to where the people were. So we are really well blended with the industry, with our supporters. And I think this is a unique thing in this community. And in this conference, I think we like to keep it that way, that it's not just that the supporters are in one corner somewhere, nobody goes there, but we really want everybody to blend together and discuss, and this is the way forwards. Here you can see another nice picture of the discussions going on. And there were plenty of these in the social media during the conference, but I think we were also busy attending the conference that we didn't have much time to follow it. At least that was the case in my case. And finally, I have to say that some of these guys, who were really doing the hands-on organization, they were doing a lot of work before the conference and during the conference. And I think they deserve a special thank you. And I'd actually like to ask Stefan and everybody who were helping in the organizations in anyhow, like a body or anybody, come on stage. I think you guys all deserve a big applause, but come here. Great. So now you can see that we put a lot of effort to this, and we'd like to continue with the successful conference next year as well, and the following years. And we like we said in the beginning, we like this to be a community-driven event. So we are actually thinking, or we are looking for co-organizers also for the conference for the next time and the following years. And if your institution, primarily now we are looking for academic co-organizers, because now it has been like company organized, but of course anybody is feel free to propose if your institution is interested in co-organizing the next conference or the following ones. Please send email to Stefan just to let us know like who would be interested in joining this, and we will also then gather feedback from you. I think you will, Stefan, revise the feedback form, or did you already do it?
It's ready.
Aha, it's ready. So basically, from the feedback that you give, we will then also see how we will realize this in the future. But as I said, the principles will probably still be the same. Maybe there will be a little bit more possibilities to attend for a little bit more scientists and people. And we are also looking for to optimize certain things. But your feedback will be very important for that. But yeah, again, thank you a lot. And I think now we have lunch still, and that's going to be on the second floor. So not right here, but on the second floor. And it's the same time for everybody. So everybody can now go for lunch. And then I hope you will have a safe trip back home and see you next year again. Thank you.